In this video, we want to take a look at parametric and vector representations of lines. In the xy plane, so when we're in R2, we can describe a line with a single linear equation, right? One equation with two variables, x and y. That will describe a line. But when you get into R3, that a similar single equation, but this time in three variables, doesn't describe a line. It's going to describe a plane. And so how do we describe a line? Now, it's possible to do with one equation. You could do something like a cylinder of radius 0, but it gets really complicated, and then you're looking at quadratic things in there, and lines should just be linear, right? They should just have first-degree things. So anyway, describing a line in higher dimensions is going to take parametric equations or vector equations. It turns out they're pretty close to the same thing. So what I want to look at here is given a point in Rn. So here's my point x0. Oops, I actually have a pencil to draw with here. Here's my point x0. And I'm writing it as vector because that would have, a bunch of coordinates, x1, x2, x3 up to xn. And I'm given a vector also in Rn. Call it vector v. So I'm going to have that pointing out this way. I claim there is a uniquely determined line that passes through this point and heads in that direction. There's one line that passes through this point and heads off in that direction. If it's a uniquely determined line, then its equation should be determined. We should be able to describe it. And so here's how we're going to do that. My claim is that any point on the line, take some point x, can be described as starting here and then moving some scalar multiple of v. Now remember, there's some coordinate system somewhere, and I'm just drawing an R2 coordinate system, but this could be, well, let's make it an R3 coordinate system, but it could be R4 or higher. And I'm thinking of both x, well, I'm thinking of x0 as a vector here and x as a vector there. And so I can get to x by first doing x0 and then by moving some scalar multiple of v to get out here to x. And notice if x is not on the line, so if x is a point over here, then moving in scalar multiples of v isn't going to get me over there. I would have to have some other direction other than v. So the claim is that this vector x can be written as x0 plus a constant times v. This is a vector equation, right? It's an equation, it's got an equal sign, and it involves vectors. This is one vector equation. But it's a parametric vector equation because it involves this parameter t. It's curious that in the textbook that we use for this class, they state this as a theorem. They say that if you have something that looks like this, you're describing a line, and if you want to describe a line, you would use something like this, that it's a theorem in R2 and R3. And then, in the very next paragraph, they make a definition so that they say in Rn, we can describe a line by doing this. Okay. Again, it's a matter of they don't know what geometry looks like in higher dimensions, so they're imposing the geometry on it. They're saying, we're going to define it to be this way. Okay, maybe it just is that way, and we're finding that that's the case. Anyway, it works the same way in all the dimensions. Let's do an example. I want the line through the point 1, 2, 3 that's in the direction of 4, negative 1, 2. So according to this, the 1, 2, 3 is the point that I want it to go through, and the 4, negative 1, 2 is the direction vector, so I can just write this. Technically, there is a vector equation of that line. I'm going to do a little bit more just to see it in a different light. So I'm going to distribute the t through. Let's multiply the scalar times that vector, just like that. Then add the two vectors component-wise, and you can see that the x-coordinate is 1 plus 4t, the y-coordinate is 2 minus t, and the z-coordinate is 3 plus 2t. If I had to write this as parametric equations, I would say x equals this, y equals that, and z equals this third thing. Notice that you can see in the parametric form the point that it goes through, 1, 2, 3. Those are the constants of the three formulas. And then if you look at the linear coefficients, they are the direction vector for negative 1, 2, for negative 1, 2. Now, when you take count 3, you learn about position vectors, and then the derivative is the velocity vector. Well, if this is a position vector, at any time t, I know where I am, then the derivative is just going to be that direction vector v, right? So that direction vector is like a velocity vector. If you're thinking of this as describing motion along that line, so that any time t you know where you are on the line, then of course the longer the vector v, the faster you're moving along that line, and the shorter the vector, you're describing slower motion. Okay. But you could write it as parametric, and in fact, if you've had a Calc 3 class, we do that quite a bit. But I think, well, we also use vectors in Calc 3 as well, don't we? Here we wanted to focus mainly on the vector form, not so much the parametric form. I mean, it's really the same thing. I'm either giving you three, well, since this problem was in R3, I'm either giving you three parametric equations, or I'm giving you a single vector equation. But of course, a vector equation, in order for two vectors to be equal to each other, they have to be equal in corresponding components. So I have really three equations here, even though it looks like I have only one. Okay. Now, another way we might be given information and want to come up with a line is if we're given 2 points. Suppose I've got the point A and the point B, and I want the line through those 2 points. Well, if I could just come up with the direction from A to B, then I could use that like the vector V in the previous section here. And I can get the vector from A to B because that would just be B minus A. Of course, I could do it in the other direction. If I wanted to move that way, I could do A minus B. But I'm going to choose B minus A from here. So my vector V is B minus A. That's the direction I want to move along that line. And so from the work above, I have that any point X on that line. Let's put X down here this time. It's going to be A plus T times that vector V, B minus A. Now the way I have it drawn, since I have to go that way, this T would have to be a negative in order to get down to it, but that works. So technically right here, we have a vector equation for that line. I want to rewrite it because this is an interesting result here. So I'm going to first of all distribute the T across that subtraction. I'm then going to reorder some things. Addition is commutative, so we can do that. So I'm going to move this over here. And then from this, I'm going to factor the A out, and I've got 1 minus T times A plus T times B. This is a really interesting form if you're given the 2 points, right? The 2 points that the line goes through are A and B. I can see both of them in this equation. And then if I multiply one of them by 1 minus T and one of them by T, then that's the same thing as doing this that we had up here. I like this form. Notice, if T is equal to 0, then B goes away and this becomes a 1. So at T equals 0, you're talking about the point A. If T equals 1, then the 1 minus 1 is 0, and the A goes away, and you're just getting the point B. If T equals a half, let's say, then this would be a half A plus a half B, which actually would be A over 2 plus B over 2, which would be A plus B all over 2, which is the average of A and B. It would be the point exactly right in the middle. So this was with T equal to a half right there. Oops, I said a half. That would be 1 half. This is T equals 0 here. This is T equals 1 over there. If you took T equals 1/4, so you'd have 1/4 B plus 3/4 A, you would be exactly at the 1/4 mark along the way. It's closer to A because A, it's like a weighted average, right? You're counting A 3 times and B once, because it's 3/4 and 4/4, and you're dividing the whole thing by 4. So it's like you're taking the average of A, and B, and you get closer to A by 3 to 1, right? So 1/4 of the way and 3/4 of the way. If you took 3/4 for T, then B would be multiplied by 3/4, and you get the point over here. In fact, any number you can see as a weighted average of A and B. It's easiest to see that weighted average if the t value is somewhere between 0 and 1. And in fact, all the values of 0 and 1 give you the line segment with the A and the B as the endpoints. As soon as you get outside of that range, so you say take t equals 2, for instance, right? This would be 2b, or would it be something else? 2b, or no, it would be 2b. And then, of course, 1 minus 2 would be -1. So this would be, actually, in this case, I see it easier here. If you plug a 2 in there, you're at A plus 2 times this vector, which would put you out here. This is t equals 2, clear out there. Any point on that line is just pick a different value of t. If you want to be out on this side of A, you have to take t negative. So for instance, if you took t as -1, then if t is -1, then A looks like a 2 and B looks, the coefficient in front of A looks like a 2 and B looks like a -1, which is exactly the reverse of what we just did. So then you end up down here at this point, t equals -1. And in that way, you can describe that whole line. I've done a lot of computer animation in my days. And there's certain things that I do where, I need, well, for instance, I have a juggler. So it's this little stick figure guy, and well, it's a stick figure. Every piece of him, except for the head, is made out of line segments, and I just need to know where are the endpoints. And in particular, when he juggles, his forearms move because his hands have to move in order to juggle the balls. And so every frame, as I generate that animation, I need to know where the elbow is and I need to know where the hand is so that I can draw the line segment. And then I just give it, I give the computer that parameterization and say, hey, I know where the wrist is, I know where the elbow is, just draw the line between them with t equals 0 to t equals 1, and it draws that line segment. It's a very convenient way to draw line segments, is using this kind of parameterization. Parameterization? Yeah. Vector parameterization? Sure, maybe better described that way. Let's do one example. Here's a line in R3 passing through the points 1, 2, -3, and -7, 2, 4. And I want to come up with parametric representation of that line. So there's my 2 points, 1, 2, -3, and boy, that looks funny. That should just be a vector there. -7, 2, 4 is the other point. And so using this formula right up here, I just have 1 minus t times the first one plus t times the second one. If you wanted to rewrite that in another way to see precisely what the x, y, and z coordinates are, right, you just have to distribute the 1 minus t into this vector, the t into that vector, and so on. It's straightforward. Just do the scalar multiplications, add the vectors, and then you can see what each component equation is. Personally, I don't necessarily need the component equations if I'm really just describing the line. So there's a bit of parametric lines. This works in any dimension. In the next video, we're going to have to look at a similar thing with planes.